3 times in recorded history, something has crossed into our solar system that did not belong here. Not an asteroid nudged out of its usual orbit. Not a comet flung inward from the outer edges of our own sun's territory. Something from outside entirely, formed around a different star, shaped by different chemistry, and passing through our neighborhood exactly once before disappearing again for good. The third of these visitors arrived in the summer of 2025, and by the time it left, it had handed scientists the richest set of data ever collected on an object from beyond our solar system, including a detection nobody had managed to make on either of the 2 visitors before it, and an estimated age so extreme that it may have started forming before the sun we orbit ever existed at all. Only 3 confirmed cases in all of human history. That number is worth sitting with for a second before going any further. Humans have been watching the sky with organized astronomy for thousands of years, and with telescopes specifically for roughly 4 centuries, tracking planets, comets, and stars with steadily improving precision the entire time. Out of that entire span, exactly 3 objects have ever been confirmed to have originated outside our solar system entirely, arriving from beyond the sun's gravitational reach and departing again just as permanently. That rarity alone explains why each new one generates this much attention among professional astronomers, well beyond whatever headlines it might produce along the way, since every single confirmed case adds meaningfully to a dataset that, until fairly recently, did not exist at all. Start with what actually makes something interstellar, because the definition matters more than it sounds. Every planet, moon, asteroid, and comet native to our solar system shares one thing in common. Gravity keeps pulling it back, locking it into a repeating loop around the sun that continues indefinitely. An interstellar object breaks that rule entirely. It arrives from outside the sun's gravitational grip, swings through just once on a path too fast and too sharply bent for the sun to ever capture it, and then leaves permanently, continuing back out into the galaxy. Confirming that an object fits this description takes careful orbital math, comparing exactly how an object's path curves against what a bound, looping orbit should look like. A gentle curve that loops back is homegrown. A sharp, fast bend that shoots straight back out again belongs to something just passing through. The first confirmed case of this happened in 2017. Small, strangely elongated, and moving fast, it tumbled through our solar system, showing almost no visible activity at all. No gas, no dust. None of the usual signs a comet gives off as it nears the sun. That silence made it maddening to study. By the time telescopes fully understood what they were looking at, it had already faded too far to learn much more, and several open questions about its behavior remained genuinely unresolved even years later, simply because there was never enough time to gather the data needed to settle them. 2 years after that, in 2019, a second interstellar visitor arrived, and this one behaved far more conventionally, complete with a glowing coma and a visible tail, acting the way scientists already expected comets to behave, based on decades of studying ones native to our own solar system. Because it was considerably more active, researchers pulled a richer set of chemical data from it than they ever managed with the first visitor. Still, both encounters left the same lingering frustration behind, the sense that a bigger, brighter, better-timed third visitor could reveal so much more if one ever showed up while the right instruments were ready and waiting. That third visitor arrived on July the 1st, 2025. A survey station in Rio Hurtado, Chile, part of a network built specifically to scan the entire night sky for objects that might threaten Earth, flagged a fast-moving point of light nobody recognized. Within days, astronomers had worked out its path and confirmed what they were looking at, an object moving far too quickly to ever be captured by the sun's gravity, destined to pass through once and keep going, permanently, back into deep space. It became the third confirmed interstellar object in human history, officially designated 3IATLAS, the number marking its place in that short sequence, the name crediting the survey system responsible for spotting it first. Here is where the comparisons to the 2 previous visitors start breaking down almost immediately. 3IATLAS traced out the single most extreme hyperbolic path ever measured for any object of its kind, more sharply bent than either of its 2 predecessors, moving at well over 200,000 kilometers per hour when first spotted, and accelerating further as it fell inward toward the sun under the sun's gravitational pull. Using that extreme velocity and comparing it against the average motion of stars throughout our region of the galaxy, researchers were able to estimate roughly how long the object had been drifting alone through interstellar space, since whatever ancient event first ejected it from its home star system, a calculation that relies on the reasonable assumption that an object drifting freely through the galaxy for a very long time will have picked up a velocity roughly matching the average motion of the stars around it. The number that came back was staggering, somewhere between 3 billion and 11 billion years. Our own sun and solar system, for reference, are about 4.5 billion years old. Depending on where within that range the true figure actually falls, It is entirely possible this particular comet is older than the star we orbit, having potentially formed around a star that lived, aged, and died long before our own sun ever ignited, leaving this frozen fragment to drift alone through the galaxy for the entire span of time since, untouched by anything at all until it happened to wander into our solar system's gravity purely by chance. Unlike the quiet first visitor from 2017, 3IATLAS turned out to be genuinely active, heating up as it approached the sun and releasing frozen material directly into space as gas, forming a glowing coma and a faint tail behind it, visible enough that ground-based observers with modest equipment could track its progress alongside the world's largest professional instruments. That activity was the whole ballgame for scientists hoping to study it properly, because an active object hands its internal chemistry directly to waiting telescopes, while a quiet, inactive one keeps its secrets locked away. Just as important as the activity itself was the timing of the discovery. Catching a 3I-Atlas. Months before its closest approach to the sun gave researchers something neither of the two earlier interstellar visitors had ever provided: genuine advance notice, enough lead time to actually schedule observing sessions on some of the most heavily booked telescopes on Earth and in orbit, rather than scrambling reactively the way earlier teams had to. Among the instruments that lined up to study it, none mattered more than the James Webb Space Telescope, humanity's most advanced space observatory, built to detect infrared light rather than the visible light human eyes perceive, which lets it pick up chemical fingerprints and heat signatures no ordinary telescope could ever detect. Webb was not originally designed with fast-moving small solar system objects in mind, and tracking something moving as quickly as 3I-Atlas pushed its systems into territory well outside typical operating conditions. Engineers managed it anyway, locking Webb onto the comet in August of 2025 for its first detailed spectrum, then again in mid-December of 2025, after the comet had already swung past the sun and started heading back out, using a different instrument tuned specifically to mid-infrared wavelengths. That second round of observations produced the most detailed chemical readout ever obtained from an interstellar object, and what it contained surprised almost everyone studying it. Compared to typical homegrown comets, 3I-Atlas showed an unusually high ratio of carbon dioxide to water vapor, breaking a pattern astronomers had come to rely on after decades of studying comets native to our own solar system. Buried deeper in that same December data was something even more unexpected: a clear signature of methane gas escaping the comet, the first time methane had ever been directly detected coming from any interstellar object. Alongside the methane and carbon dioxide, Webb also confirmed water vapor streaming off the comet, plus a genuinely surprising atomic signature belonging to nickel, a metal whose presence tells researchers something specific about the raw ingredients mixed into this object when it originally formed, likely billions of years ago, around a star system entirely unlike our own. The methane detection deserves special attention because methane is a notoriously fragile molecule under the wrong conditions, one of the simplest hydrocarbons known and among the easiest to chemically break apart when exposed to enough energy over a long enough period. Bombarded by raw cosmic radiation for billions of years, exactly the kind of unshielded exposure an object drifting alone through interstellar space would face constantly with nothing at all to protect it. Methane should, in theory, have broken down and vanished from the comet's outer layers long ago, converted into other, more stable compounds by decades upon decades of relentless radiation exposure. Finding a strong, unmistakable signal of it escaping the object forced researchers to rethink where it was actually coming from, rather than simply logging the detection and moving on to the next data point. The leading explanation now is that the comet's outer surface had indeed lost most of its original methane over billions of years of radiation exposure, exactly as expected under standard models, and that what Webb picked up instead was methane escaping from deeper, previously shielded material beneath the surface, material only now being exposed as the outer layers boiled away in the heat of the sun during the comet's brief close approach. Webb, in other words, was not simply reading the surface of this ancient visitor. It was reading material that had been sealed away, completely untouched, since long before our own solar system existed at all. Material that had essentially sat in deep cosmic cold storage for billions of years before finally, briefly, becoming readable to any instrument at all. Webb had plenty of company throughout this effort. NASA's Hubble Space Telescope observed the comet both shortly after discovery and again following its closest solar approach, helping researchers estimate the size of its solid nucleus, the actual rocky, icy core buried beneath the glowing coma. Measuring that core accurately is difficult, since the tiny solid nucleus is almost always drowned out by the far brighter cloud of gas and dust surrounding it, forcing scientists to rely on careful modeling, combining brightness data across multiple wavelengths with assumptions about surface reflectivity. Those estimates shifted as more observations came in, starting with a fairly broad early range of possible values and narrowing down considerably once the Comet S activity settled following its closest solar approach, eventually settling around 2.5 kilometers across, noticeably larger than either of the two previous interstellar objects, and a major reason 3IATLAS became bright and active enough to study in such depth. A larger nucleus means more surface area available to heat and release gas, which in turn means a brighter coma and a cleaner signal for instruments like Webb to work with. A straightforward relationship that made this particular visitor considerably more forgiving to study than either of its two smaller, fainter predecessors. Other instruments filled in the remaining gaps. SphereX, a space telescope built to survey the entire sky in infrared light, observed the comet in December of 2025. And picked up a rising activity following its closest solar pass, along with dust made of tougher, heat-resistant material and additional gas signatures. Ground-based radio observations using ALMA detected still more molecules escaping the comet, including methanol and hydrogen cyanide, while separate visible light spectroscopy independently confirmed gas phase cyanogen and atomic nickel, corroborating what Webb had already found through an entirely different technique. Given the object's extreme trajectory and surprising age, some online speculation inevitably wandered toward the idea that it might not be natural at all, drawing on its unusual size, unusual chemistry, and record-breaking orbit as supposed evidence for something more exotic. Rather than brushing that question aside as unworthy of serious attention, scientists actually checked it directly, using radio telescope arrays built specifically to hunt for technosignatures, meaning any artificial radio signal that might suggest deliberate construction rather than natural formation. An approach with decades of precedent in the broader search for intelligent life beyond Earth. Those instruments listened across a wide range of frequencies throughout the comet's passage through our solar system, covering the entire window during which any hypothetical signal might plausibly have been transmitted. Nothing artificial turned up anywhere at any point across any of the frequencies searched. Every measurement gathered, from Webb's chemistry to Hubble's imaging to the dedicated radio searches, matched precisely what a genuine, ancient, natural comet should look like. Unusual by the standards of our own solar system's comets, certainly, given how different its carbon dioxide, methane, and nickel signatures turned out to be, but entirely explainable as an icy body that simply formed under different conditions around a different, long-vanished star, rather than requiring any explanation beyond ordinary, if genuinely ancient, cometary physics. Zoom out from the chemistry for a moment and consider what this kind of discovery actually offers science more broadly. Every interstellar object researchers get the chance to study up close hands them a direct physical sample of material built somewhere else in the galaxy entirely, something no telescope pointed at a distant star could ever provide on its own, no matter how powerful. 3 confirmed opportunities like this exist in all of recorded human history, and 3IATLAS produced by far the richest dataset among them, a direct consequence of its larger size, its stronger activity, and the sheer advancement of the instruments available compared to what existed back in 2017. 3 confirmed detections within less than a decade, especially with detection technology still improving every year, has pushed the scientific community toward taking seriously the idea that these wandering visitors may be far more common throughout the galaxy than anyone previously assumed, simply going undetected for lack of adequate tools and timing until quite recently. That shift carries real consequences for what happens next. Newer, more sensitive sky survey telescopes are already coming online, purpose-built to scan enormous portions of the sky every few nights, with a level of sensitivity earlier systems never had, covering ground that older, narrower survey programs simply could not match. Researchers broadly expect detection rates for interstellar objects to climb meaningfully in the years ahead, shrinking the gap between an object's arrival and its confirmation, and giving astronomers even more advanced notice than the several months of lid time 3IATLAS provided. More lid time means richer science every single time, letting teams schedule Webb, Hubble, and every other major instrument well ahead of an object's closest approach instead of scrambling the way researchers had to back in 2017, when there was no warning at all before the very first known visitor of this kind had already begun fading from view. 3IATLAS, in that light, may not be remembered as some singular, unrepeatable event confined to the history books as a one-time curiosity. It may end up marked instead as the third entry in what eventually becomes a fairly routine stream of ancient interstellar wanderers passing quietly through our neighborhood, most of them still going entirely unnoticed, simply because nobody yet has the tools sensitive enough to catch them in time, waiting somewhere out there for the next generation of survey telescopes to finally give them away. None of this came together by accident, and it is worth acknowledging the sheer logistical effort behind it. A single asteroid hunting survey network in Chile made the initial catch, a system built primarily to protect Earth from hazardous impacts rather than to hunt interstellar visitors, which made the discovery itself something of a fortunate byproduct. From there, confirming the object's true nature required astronomers on multiple continents comparing orbital calculations within days of each other, space agencies coordinating observing time across different telescopes and instruments, and ground-based radio arrays contributing yet another layer of chemical detail entirely, separate from anything the space telescopes could provide. Very little of that coordination happened publicly or dramatically. It played out mostly through scheduling emails, shared datasets, and quiet agreement among research teams who all wanted the same outcome, squeezing as much verified information as possible out of a visitor that was never going to give anyone a second chance. Step back far enough, and the full arc of this one object's journey becomes almost impossible to hold in your head all at once. It formed billions of years ago around a star that may not even exist anymore, somewhere in a completely different region of the galaxy, condensing out of the same kind of disk of leftover material that builds planets and comets around any young star. A process astronomers understand reasonably well from studying young stellar systems still forming within our own galaxy today. At some point, a gravitational disturbance, perhaps a close pass by another star entirely, flung it out of that system for good, sending it drifting alone through the emptiness between stars with nothing left to orbit and nothing left to warm it. For possibly billions of years afterward, it tumbled silently through that darkness, its original chemistry locked away and untouched the entire time, indifferent to whatever else was happening across the galaxy during that unimaginable stretch, indifferent to the birth and death of countless other stars and planets it never came anywhere near. Then, purely by chance, its long, silent path happened to bring it close enough to our sun for our solar system-S gravity to bend its trajectory and for our telescopes, finally, to notice. It swept past, warmed just enough to release a portion of that ancient material into space, gave our instruments their brief window to read what they could, and then continued on its way, most likely never to be seen by anyone again, human or otherwise. Telescopes have existed for roughly 400 years of human history. Space telescopes capable of reading a comet's exact chemical fingerprint have existed for only a few decades. Out of billions of years spent drifting through the galaxy in total silence, this object happened to pass near our sun during the one narrow sliver of human history when we finally had both the knowledge to recognize what it was and the technology to actually read its story before it disappeared again for good. An alignment of timing so improbable, it is worth sitting with for a moment longer than the headlines usually allow.